Okay, so couple of updates. So we're going to have a midterm next Monday. There will be no class next Monday. The midterm will start at 6:30. You will have 75 minutes. You will have about 5 questions or so. And you should know which section you should be going to, right? I think it was posted on Piazza. I don't remember whether it was posted on Piazza. I'll also post it on my website. And it's also posted as in the midterm review lecture, right? So please know which section you should be going to. As I mentioned before, for those of you who have classes at 6 and you finish at 7:30, you can come to your section at 7:30 because we do have the rooms up until 9. But again, the midterm, I don't want to have a midterm which is long, so it's really 75 minutes, 1 hour and 15 minutes. Any questions? And as I mentioned before, you know, I'm not going to be asking you to do anything on the midterm that we haven't covered. Just basically look through the slides, understand there's going to be a few questions on neural networks. And I mentioned before, know what is a dropout, different regularization techniques, how do you compute the gradients, what are different loss functions are, what is the cross entropy versus least square estimation, things of that sort. Batch normalization, you know, and know basic properties of probability distributions, such as Gaussians and maximum likelihood estimation and such. Okay, and we will post on Piazza which section you should be going to. Please go to correct section because one room is larger and the other room is smaller. So we want to make sure that everyone has enough space. Okay, and we'll cover everything up to, the midterm will cover everything up to the graphical models. So today we're going to talk about restricted Boltzmann machines. This is not going to be on your midterm. Okay? Questions? Yes?
I think you mentioned when we were talking about batch normalization that you thought of it as a type of regularization.
Right.
Did you ever, is it too heavy to do batch normalization to regularize with weighted data?
No, people do. People do batch normalization. They also do dropout and L2 regularization. So. Okay, so today we're going to basically, in the next few lectures, we're going to start looking at unsupervised learning, right? So far with neural networks, convolutional neural networks, you sort of, we've looked at supervised learning, right? Trying to map inputs to the outputs. So today we're going to look at unsupervised learning. We will only have some inputs X. Oh, by the way, before I forget, the second assignment is going to be out on October 9th. Okay? So it's going to be out on Gradescope. You should be able to get it and start working on your second assignment. Second assignment, same thing, 2 weeks. There's going to be, you know, analytic part where you have to write stuff, and then there's going to be the coding part. Also, I would encourage everyone to use LaTeX. If possible, right? I know there's been some discussions on Piazza. We are graduate students, so you should be able to, you know, because it's easier for TAs to mark and less confusion, and you know, it's good for you to get used to using LaTeX, particularly if you're thinking about writing a thesis or papers or going into PhD work, doing PhD studies. So let's make sure that you are using LaTeX. Okay, so unsupervised learning, we only need the inputs X for learning. We actually don't have targets Y, right? So here you can think about, you know, what can we do with it? Well, we can try to figure out, can we extract some meaningful representations from the data, maybe some features. You can think about leveraging the availability of unlabeled data, because unlabeled data is cheap to get. Maybe in many cases, people actually use data-dependent regularization for training, right? So trying to look at some form of log P of X as an additional regularizer, like unsupervised pre-training that we briefly mentioned a couple of classes ago. So we will consider 3 models for unsupervised learning, and these will form the basic blocks for a lot of deep learning models. Today, we're going to look at restricted Boltzmann machines, and Boltzmann machines and undirected graphical models in general. And then in the following few lectures, we're going to look at autoencoders. And we're also going to look at sparse coding models. These models have been around for quite some time, late 90s, early 90s. But it's good to understand what they are, because a lot of deep learning models are built on top of variants of these models. So, distributed Boltzmann machines. We've touched upon this, I guess, in our last class briefly. So let's remind ourselves what this particular model is. You have an undirected bipartite graphical model, right? You have stochastic binary visible variables x. Okay, so think of them as pixel intensities, binary, and we have stochastic binary hidden variables h. And again, you can think of them as stochastic random variables, Bernoulli random variables. And I can specify the energy of the joint configuration this way. Okay, so here you basically have Wij, so Wjk, right? This connection here, Hjxk. So this is modeling dependencies between every single pixel and every single hidden state. Obviously, you can make these models be convolutional. Later on, I'm going to show you when we start looking at deep Boltzmann machines. You can make these models be convolutional, so you can effectively have a generative model that is convolutional. And people have shown some interesting results using sort of convolutional architectures for this model. But for this particular task, or for this particular class, we're not going to look at the convolutional models. And I think for your second homework assignment, you will play with these models yourself. Okay, you'll sort of train them, look at the likelihood objective, and so forth. Now, the probability of the joint configuration is given by the Boltzmann distribution, right? It's e to the negative energy of the joint configuration divided by the normalizing constant, right? And again, this is what's called partition function because it requires summation over all pixels and over all hidden states, right? So it's an exponential sum. And it's an exponential sum because if you have, let's say you have MNIST images which are 28 by 28, there are 784 numbers. Each pixel can be on or off, so there are 2 to the 784 possible configurations, right? So you can see that that's a pretty large space. So restricted Boltzmann machine, you can also view it this way. You have a hidden layer, binary units. W is going to be our connection parameters of the model. X is going to be the visible layer, and we're just going to start with binary representation, right? Later on, we'll extend it to other types of distributions, but let's stick to the binary, the easiest possible model. And again, just to write down explicitly, we can say the joint probability has this Boltzmann distribution, right? The energy itself, the negative of the energy, has this particular formulation, which is in matrix form. It's H transpose Wx. Right? H is the set of hidden variables, X is the set of visible pixels, since everything is connected to everything. And then you have these bias terms, C transpose X, which is the biases for every single pixel in X, and B is the bias for the hidden states. Okay? And as I mentioned before, sometimes the joint, you can think of it as a log linear model, because if you take the log of the joint, it's going to be linear in the parameters, right? That's why these are called log linear models. Or I can write down in terms of product of these factors, right? I can say, well, there's a joint pairwise factor, and then there is unary factors. Sometimes, these terms would be called pairwise potentials, and these terms would be called unary potentials, right? So, and here we're specifying a particular form. And again, in this case, H and X are Bernoulli random variables taking values 0 or 1. People have also tried scaling it to, or sort of adapting it to the setting where you have -1 and 1. You can do that. So this notation is based on the energy function, and it's basically an alternative to the representation of the product of factors. Right? Remember, in the last class, when we looked at undirected graphical models, there are two kind of views, right? One is in terms of product of non-negative factors, another one in terms of the energy, but two are equivalent. So now, if I look at specifically at restricted Boltzmann machine, right? Here's one particular example, just to make it very clear. x1 up to xd are your Bernoulli observed variables, 0, 1s. H are your hidden variables. So I can write down the joint probability as the product of these factors, right? It's a product of all pairwise factors and all unary factors. For example, for your second homework, you're going to be training this particular model. X would represent pixels in your image, right? These are going to be binary pixels, 0s or 1s. H would represent hidden variables. Again, these would be 0 or 1s. And you can say the joint probability given parameters W, C, and B for any configuration of X and H, its probability is going to be given by this expression. Okay? Again, these are pairwise and these are unary factors. And so, this is kind of, it's more of the visualization here is done more of a, specifically how you actually view this model, right? So in the case of MNIST data set, D would be 784. You would have 784 inputs here. And let's say you're building a model with 100 hidden variables. So H, capital H, would be 100, okay? So the matrix, the parameter matrix that you're going to be learning is going to be of size D by H, right? Which is the matrix W there. Sometimes there is also alternative way of viewing it. It's called factograph representation. For pairwise MRFs, it's probably not very informative. But if you're interested in going, and studying high order potentials, like third order potentials, then this representation might be a little bit easier to draw. But we won't care about this particular representation too much. Inference. So let's see how we do inference in this model. So what is inference? Inference is going to be the case of given the states of observed variables. So if I give you an image here, what's the distribution of the hidden variables, right? How many of you are familiar with expectation maximization algorithm? A few, right? So in EM algorithm, which is a basic algorithm in machine learning for dealing with latent variable models with latent variables, the very first thing you need to do is you need to figure out what's the distribution of the hidden variables. And that's going to be important for us to learn parameters in this model, right? So let's see how we can do inference. Notice that there is no interactions between hidden variables. And according to undirected graphical models, and if you look at the Markov blanket, you can say the posterior over the hidden states, given the data, factorizes. And you can just read it off from the Markov blanket assumption, right? If you look at these two hidden variables, hidden variable 1 and 2, they become independent, conditioned on the data, right? The state of one is independent of the state of the other. And I think in your homework, I believe you will go through the math and actually prove this properly. Not just by reading it off the graph, but actually going through the derivations and actually showing that this posterior factorizes. It's very easy to compute. And we'll show what this computation is. It turns out that these conditional probabilities are just simple logistic functions. Same thing for P of x given H. Once I tell you the states of the hidden variables, you can compute the distribution over the observed image, over the observed pixels, right? So that's why sometimes these models are called generative. They're called generative because if I tell you what the state of the features are, I can actually generate the image for you. Right? I can sample the states of pixels and you can actually see, is the model generating a 6 or a 9 or whatever image it's generating. So let's look at the conditional distributions. We're trying to infer conditional probability of H given X. The conditional probability that Hj takes value 1 is going to be given by this logistic function. Right? In fact, if you look at this particular model, this conditional probability, it's exactly the same thing as what you would do in a neural network with logistic or with sigmoid nonlinearity, right? It's exactly your homework one. When you say, here's my pixels, how do I instantiate hidden states? with sigmoid nonlinearity, that's what your equation is, right? It's like a feed-forward pass in the neural network. But notice that in this particular model, whereas in neural networks, you instantiate the hidden states using sigmoids, these are deterministic. According to this model, this conditional probability is the probability. So it tells you what's the probability of the hidden state taking value 1. It's a sigmoid. And alternatively, the conditional probability of x given h is given again by the product, because they become independent. And now the conditional probability that x takes value 1 is also given by the sigmoid. So it's almost like, you go up and then you go down. Right? So you design these conditional probabilities. From the joint, you can always figure out what the conditional probabilities are. And again, it's also given by the sigmoid. Any questions? So this is something that's pretty straightforward to derive from these classes of models, right? And again, it's just given by the sigmoid. And you can see that the sigmoid, it's almost like you're transposing. It's the, when you're generating x, it's the column of w. When you're generating h, it's the row of w, right? So it's symmetric. W is, it's almost like transpose of another one. Markov property. So how do you actually derive? It's a hint for you. How would you derive the conditional, that these conditional probabilities factorize? Well, you can always say, what's the conditional probability of some variable zi conditioned on the whole bunch of other variables in your graph, right? So the conditional probability of some latent variable zi or some random variable zi given its neighbors, right, is the same as the joint divided by the marginal, right? So that's the expression, the second expression here. It's the joint divided by the marginal. And you can say, well, what's the joint? Well, the joint is the product of all the factors involving zi and any of the neighbors of zi, right? That's the joint. The marginal, it's the same product, but you're marginalizing over zi, right? Over the states of zi. In our case, zi's are going to be Bernoulli random variables. So whenever you do summing over zi, you're going to be doing summing over two things. When zi takes value 1 and when zi takes value 0, right? And zi is any variable in the Markov network. So here's hk or xk or hj in an RBM, and the neighbors are the neighboring of zi, right, in the Markov network. So it's easy to derive these conditional probabilities. And that's how you would derive that these conditional probabilities are given by the sigmoid. Right? Okay, now, there is another concept known as a free energy. So when you look at some literature, particularly looking at these kinds of models, sometimes people call about free energy. Which is related to computing the marginal distribution of P of x. So let's look at the derivation. So it turns out for these kinds of models, you can actually compute P of x by summing out over the exponential number of hidden variables, right? You can only compute it up to normalizing constant, but you can sum out the states of the hidden variables. So let's look at how you actually do it. So the first sum is the sum of all hidden states that take value 0, 1, and there's h of them, right? H typically would be a large number, like 100 or 500. Sometimes people build model with like 2,000 hidden variables. So there are 2 to the 1,000 possible configurations, right? So obviously that space is exponential. But it turns out there is a trick to do it. So here we're summing over the energies. So one of the things that you can do, and the reason why you can do it is because of the conditional independence properties. Condition on x, h has become independent. Right? So given x, you can actually push this sum, right, inside the exponent. Right? And then you're going to be summing over all the states, j equals 1 to h, of log of 1 plus x to bj plus, stuff. So where is the second term comes from? Where is this coming from? Well, this coming from the fact when hj takes value 0, you're just going to end up with 1. When hj takes value 1, you end up with this factor. So you can go through the definition, it's just a little bit of algebra, and plug in values of 1 and 0. And this term here is known as the energy. Right? So here using property, using conditional independence property, in order to be able to compute this exponential sum, because you can push it inside expectation. And I would encourage you to actually do this derivation yourself. It's not very complicated, but it requires a little bit of algebra. But nonetheless, what you can do is you can sum out the states of the hidden variables, and so now you can represent the marginal probability as the negative of the free energy divided by the partition function. So these quantities are quite important because sometimes people relate free energy to the marginal, and that can tell you something about the model. We'll see later how we're going to be using free energy, in particular for evaluation of these models. Oh, actually, sorry, I actually give you the derivation of how you can do it. I thought I didn't, but apparently there is a derivation. So here's your derivation of how to compute the free energy. Right? So here's one trick. I don't want to go through the whole derivation. It's pretty straightforward, but here's one trick. When you're summing out over the states of h, right? So you're summing out over h1, h2, all the way up to h sub h of this quantity here. What you can do is, because of the independence property, because the conditional independence, here you can break it down into the individual sums, right? And then you can sum out over the two states. When h1 equals 0, when h1 equals 0, you basically get b1. When h1 equals 1, you basically get the other term. When h1 equals to 0, you just basically get 1, right? Because the exp to the 0 is 1, e to the 0 is 1, and then for the second one, you get this term. So that's why you have this term 1 plus exp to the other one, right? Because that's just the sum of the two values of h1 being 0 and 1. And then you can just break it down, put it together, and you basically get this expression here. One thing I want to point about this particular model is that if you look at this model, the marginal probability distribution is no longer has this log linear form. In fact, if you look at this particular formulation, and if you bring this this summation out of expectation, you can write it down as a product of the whole bunch of functions, right? So the marginal probability is kind of product of a bunch of things. And we'll later come back to have a little bit of intuitive explanation what this thing is doing. Right. And that's exactly, as I mentioned, sometimes it's also known as a product of experts model. Because you have product of a bunch of functions that depend on x. It's not a mixture-based model, like mixture of Gaussians or clustering. It really is a product model. Okay? And that's very clearly written by, the product of a bunch of these terms. And later on, we'll see why this is an important property for this model. Okay, so sometimes this particular formulation of log 1 plus exp is known as a soft plus. And soft plus has, this particular representation, right? It's almost like rectified linear union, right? Here's a ReLU, and here's a soft plus, right? In fact, there's been a few papers where people tried to use soft plus because it's differentiable as opposed to using ReLUs. But the only problem with soft plus is that you have too many logs and exps, which really slows down computation. So that's why in practice people use ReLU, because it's much easier computationally. It's a differentiable function. It's obviously, you can see, has the same kind of shape, but computation is very expensive. So here is the bias, the probability of each xi, bias of each feature, and is a feature expected in X, right? So this tells you about something about bias of each feature, and this is telling you something about expectation of existence of a particular feature in the data. So let's see how we can do, so so far we've looked at the joint probability model, we've looked at conditionals, we've looked at the simple property of marginalizing out the hidden states and look at the marginal probability up to normalizing constant. Let's look at what this model can learn. So if you apply this model to these handwritten characters, you will learn these, this kind of structure, right? A lot of that structure looks like an edge-like structure, right? For your second homework, you'll train this model on MNIST dataset, and you should see something like that as well. Kind of features like what you're seeing here. And if I give you a new image, and again, as I've shown you in the last class, you can say, well, it's a linear combination, effectively, of a whole bunch of features, right? That's the conditional probability, where these numbers are given by the probabilities of existence of each particular feature. That's an intuition. It's almost like a reconstruction. Given the input, you figure out what features should exist. Given these features, you can reconstruct back the original input. So that's just an intuition of what the model is doing. But how are we going to be using this model? Well, given a new image, we can compute its conditional probability, and then we can use the vector of conditional probabilities as the feature, right? So you can plug in the classifier, you can start building a multi-layer model out of it. Now, how do we do learning in this model, right? And that's generally true for all types of undirected graphical models, conditional random fields, Markov random fields. How do we learn parameters of this model? So let's say we're given a set of ID training examples, and we want to minimize the average negative log likelihood, right? Or we want to maximize log likelihood. So in terms of, we're going to be looking at the loss function. Right? So what we're going to do is we're going to try to minimize the average of the negative of the log of the probability. So we can write down the derivative of the negative log likelihood objective. So we can say, here's our likelihood objective. If I differentiate with respect to the parameters of this model, parameters of this model being W, the bias terms, we're going to end up with this expression. Okay? And it's kind of interesting because when you look at the log, you sort of have these energies, right? So you have the difference between two expectations. Let me just see. And this is sometimes called positive phase, and this is sometimes called negative phase, which is hard to compute. Okay? So the first term is the expectation with respect to the conditional probability. So this expectation is the expectation with respect to the conditional probability of H given X, right? The second is expectation with respect to P of X and H. The problem with the second expectation is you can't really compute because you don't know P of XH, because you don't know the normalizing constant, you don't know the partition function. Okay? We're going to look at precisely what these terms are doing. But this is generally the learning rule for any type of undirected graphical model, right? If you've ever worked with conditional random fields or Markov random fields, you get this expression. Let me just see. Right. So here, what we're effectively doing is, this is just, I'm saying that this is an expectation with respect to P of X, P of H given X, right? So how to compute this? Well, you first compute the distribution of H given X, and then you take an expectation with respect to this distribution, right? Condition on X, P of H given X fully factorizes, right? As I mentioned before there. So each individual factor is very easy to compute, right? It's the probability of it being 1. Hj takes value 1 is just a sigmoid. So once you have this factorization, it's very easy to compute this expectation because they're all independent, right? The second term is intractable because of exponential number of configurations. So if you really wanted to compute the second term, you would have to write down sum of all possible configurations of X. of your data, right? So that's an exponential sum. You can't really compute it. We have to use some approximation or some approximate algorithms for estimating the second expectation. Any questions? I think that in your homework, it would be good for you to derive this learning rule, this derivative of the log likelihood objective. It's very informative, and it's true for, again, for any type of undirected graphical model, not just restricted Boltzmann machine. Okay? And we'll look at the derivative of the energy function with respect to the parameters. This is fairly straightforward to derive. You can just write down the log likelihood function, take the derivative. You're going to have terms whenever you're differentiating a log of something, you get 1 over that. And then you look at this expectation, you just writing down what that expectation is, and you will figure out that you have essentially these two terms. Okay, now how do you train this model? Okay, one of the problems with this particular formulation is that how do you estimate this expectation? How do you estimate the second expectation? It's generally very difficult to do. But there is one particular idea. It was contrastive divergence. It was developed by Jeff Hinton back in 2002. And it has one specific property. It's a very successful algorithm for training in general undirected graphical models. But the key idea is you're going to be replacing expectations by point estimate at some value x star or x bar. And you're going to be obtaining this particular point by doing Gibbs sampling. Okay? And you're going to start your Markov chain at particular location x, where xt is some data point. So you're going to run a Markov chain when you start at a particular data point. I'll make it more precise exactly how you do it. But here's the idea. It turns out that implementing this idea really requires 4 lines of MATLAB code, 4 lines of Python code. Very simple. So what you do is you do the following. You start at the data, xt, any data. Say you try to train your model using mini batches of size 100. So you start at the data. You sample the states of the hidden variables, p of h given x, which you know that this is conditional probability is given by logistics. Then you resample back the original data, x, right? And then you proceed. You again sample the states of the hidden variables. You sample the states of the observed variables, sample the states of the hidden variables, and so forth up until some time step k. So, people sometimes use one-step contrastive divergence, which is just one up and down pass. Or sometimes people use 10-step or 5-step, which basically means you have to do it 5 times. And you get the sample x tilde. Okay? So think of x tilde here as a sample from the model. Obviously, it's not the correct sample, but it's an approximate sample from the model. You start with the data and you corrupt the data. You can also think of it as you start with the data and then you essentially corrupt your data. And you say, well, these are negative samples, these are positive samples. Positive samples is what I see in the data, so I want to raise the probability of it being more probable. What I get as a corrupted version, I don't see in the data, and I want to lower its probability, right? So I want to raise the probability of xt, and I want to lower the probability of x tilde. That's basically what this learning rule is doing, what this algorithm is doing, right? So let's look at it more precisely. If I have some energy, and remember, energy is negative of log of the probability, right? So high energy is bad, low energy is good, right? So if you have some energy landscape like this, what happens here is that you start at your data, you infer the states of the hidden variables, and then you say, well, this is my sort of observed data, right? I want to lower its energy. I want to make it more probable. And as I sample my model, I instantiate hidden states, visible states, hidden states, visible state. This is essentially corresponds to a Gibbs sample, a simple Markov chain. I'm going to get to some state x tilde, h tilde. And what I'd like to do is I would like to raise the probability, raise the energy of this state, which basically corresponds to lowering the probability. And that's exactly what this equation is doing for you. So now let's look at what's the first expectation is. Well, the first expectation is really if you just have a single point. If you just have a single point, then it's just the derivative of the energy of x and h tilde with respect to the parameters. This term here. Right? Because remember, you take an expectation, you could average over multiple samples. In fact, you can actually do it analytically because all the hidden states are independent. But for clarity, let's just say you sample one hidden state. That's the energy. And then when you say what's the energy of the second term, or expectation of the derivative, well, this is just derivative of the energy at this point. Right? So if you look at the log likelihood objective, you're really trying to lower the energy for the positive phase and increase the energy for the negative phase. Okay? And now if you look at these quantities, derivative of the energy with respect to parameters, remember the energy is linear in the parameters. So it's going to be very easy for us to compute these derivatives. Right? You just have pairwise, you have pairwise terms, linear terms, unary terms. So it's very easy to compute these derivatives. But that's the intuition behind positive phase and negative phase. It's very intuitive. It really is saying what I see in my data, I want to make it more probable. So I want to lower the energy. If I perturb my data by running a Markov chain, so I get away from my data, then it's a fake data. And for the fake data, I want to increase the energy or lower the probability. Right? Ideally, for this particular learning algorithm, I would really like to sample from the model. Right? I would really like to compute these expectations perfectly, so I can just sample anywhere in the space and do that. But here, we're just using approximation by using k-step, contrastive divergence, which is start at the data, run Markov chain, up and down sampler, up until you hit some point, and you just increase the energy. And that's exactly how you should think about it. In the probability space, now it's the reverse graph. In the probability space, if I see this particular digit and I look at its hidden states, I really want to increase the probability. If I start my sampler, I run my sampler, so I corrupt my data, and this is what it's going to look like. I want to lower the probability. Right? I want to say this thing should have high probability, this thing there should have low probability. Yes?
Why the sampling will crop the image?
It doesn't necessarily has to crop the image, but as you sample from the model, you're basically saying it doesn't, during learning, as you're learning, you're hoping that P of X, your model, will actually look more like your real data. In fact, if you look at the learning rule, the gradient is going to be 0 when the two expectations are matched. When these two things are the same, you have the learning rule. Or you have the 0 gradient. Right? So what happens is that you're basically saying, I want the statistics of this thing to match the statistics of this thing. And the only way for it to do it is to lower the probability of these random images and increase the probability of what you see in the real data. Right? Initially, when you start with a model, your model is going to be random. Right? So you sample from the model, you're going to see basically a lot of noise. As you keep training this model by using this rule, it effectively will start concentrating its mass on the real digits and lowering down the probability of these images to some small value. Right? And again, just as a reminder, P of X is just the negative of the energy, right? So sometimes you have to get used to, some people like to talk about energies. High energy is bad, low energy is good. Particularly if you come from statistical physics background. Some people like to talk about probabilities, right? So more intuitive. Yes?
So at the beginning, the model is like the random one, there are like two factors like more close together, those two.
No, those two would actually be far away from each other initially, right? Because initially when X, you see like a real 2, and you suddenly infer some hidden states. But if your parameters are random, as you start going up and down in the Gibbs chain, the model will start generating random stuff because it basically will say, well, any random image is a good image. They're all probable. And as you start going through the process, you'll start shaping your energy landscape so that you only have high probability on real data and low probability everywhere else. One of the big challenges in general for generative models, all generative models, is that if you look at this image, it's a 28 by 28 image, binary image, but there are 2 to the 784 possible configurations, right? So generally with generative models, you typically have this big exponential space. And the subspace where you have true data is very small. In fact, it's exponentially small, right? So how do you learn densities in that space? It's a very challenging problem. So sometimes people would say MNIST is an easy problem. Yes, it's an easy problem for classification. But if you're actually trying to build a very good generative model of characters, handwritten characters, I'm not even saying about images. It's very hard to build good generative model of images, realistic looking images. And there's some work in that space. It's a fairly difficult task, right? Okay, so let's look at the learning rule. How do we actually derive learning rule? Well, if we actually look at the energy with respect to parameters jk, then we just look at derivative of the energy with respect to wjk, which is just hjxk, right? It's very simple. So the learning rule of the energy with respect to w is just hx transpose, right? So it's hx transpose, and the reason why is because w is of size d by h, so this is going to be of size d by h. You just have to match the dimensions, right? So it's very easy to compute. It's just matrix multiplication. Let's now derive this quantity here, right? So when you say, how do we compute the expectation of the conditional probability of the energy with respect to the parameters, right? One thing, as I've shown you before, is you can just use Monte Carlo approximation. You can sample h from the conditional and just look at the derivative, right? But what you can actually do, you can compute this expectation. So you can say, what's the expected value of the conditional hjxk? Well, it's just the sum, because conditional on x, all the h's are independent. And if all the h's are independent, then you're just basically looking at summing over hj. You ignore all the other h's, because sum over all the other h's is just going to be 1. And so you look at this property, which is just given by hk and then the conditional probability of hj given 1. Right? So what does that mean? That basically means that when you compute this expectation, you don't need to sample. You just compute h of x, where h of x is just a sigmoid multiplied by x. Right? So in the positive phase, if you actually look at the code, it's like one-liner. Given the data, you infer the states of the hidden variables. You don't sample them. These are just probabilities. You have a vector here. You have a vector here. You take the outer product of those two vectors, and that's your derivative. Right? Everybody sees that? It's extremely simple. It's just two, given the data, let's say given an MNIST digit, you infer the hidden states. That's a vector. That's a vector. You take the outer product of these two vectors, and that's the gradient. And that, again, just comes out from the definition of conditional expectation and the fact that the conditional expectation factorizes over hidden states. So we can write it this way. And then the gradient of this conditional probability, again, this is easy to compute. So this expectation is just this term over there. Right? This is now, by definition, you have to sum out over all the states of the observed variables and hidden variables of hx x transpose, and given its conditional probability. Right? And so it's difficult to compute, and as I mentioned before, we can't really do it. So this is where we use contrastive divergence. We sample x bar by running a Gibbs sampler, and then given this x bar, we just compute this conditional expectation. Right? So this particular thing what we're going to do is we're going to replace the average over all possible in configuration just by running samples. So you're basically running a Gibbs chain starting from observed data. And this is how the Gibbs chain looks like. You initialize your chain at the data. That's important. You sample X naught from the conditional probability, which is, again, just a bunch of logistics. You can sample from it. And then for T iterations, T is the number of contrastive divergence steps. Typically, it's 1 or 3 or 5, depending on how much compute you have. You just sample X from the conditional, sample H from the conditional, and just repeat it a few times. Now you get a sample. Once you have a sample, you can compute this expectation, because you're no longer looking at this exponential sum. You're just replacing sum with samples. That's a Monte Carlo approximation. So how's approximate algorithm actually works? You have the data, you infer the hidden states, you sample the hidden states, you sample the observed states, you sample the hidden states, and then you go ideally all the way up to infinity. Because at infinity, you will get the exact samples from the model, right? And that's why doing proper maximum likelihood learning in these models is difficult. Because in order to be able to sample, in order to be able to get samples from the model, true samples from the model, in order to figure out where the model is assigning high probability, where is it assigning low probability, right? You'd really want true samples from the model to say, this random image has a high probability, which is really bad. So you can take this into account, right? But contrastive divergence idea is basically simple. Instead of running it to infinity, just running it for one step, right? So, and there is a little bit of justification for contrastive divergence, but it really is just running your Markov chain for one step, which is extremely simple, right? Given the data, you infer the hidden states, you reconstruct the data, you infer the hidden states, and that's it. You have, positive X, you have negative X, and you can do the update. It's almost like what you would do in the autoencoder model, right? In an autoencoder model, given the X, you infer the states, and then you reconstruct back the X, and you're trying to figure out what's the difference between the two. Here, the learning rule is a little bit different, because you're not trying to reconstruct X, but you're really trying to characterize distribution over reconstructions, right? It's like given the X, which is the distribution, you try to reproduce this X bar, which is reconstructed distribution, and you're trying to match the two, essentially. Okay, so how does the learning work? Given X and X tilde, the learning rule becomes as follows. You basically take the gradient of the negative of the log likelihood objective. You can write it down as a difference between two expectations, right? The data-dependent expectation and model-dependent expectation. And notice that the gradient is going to be 0 when the two match, which basically says your model perfectly models the distribution over the data, right? And you take the gradients with respect to parameters and gradients with respect to the parameters. So now, in this case, X tilde is a sample from the model, right? That's the trick. That's the key thing. It's a sample from the model where you can use contrastive divergence. And then this is the update rule. That's all. Once you have X, once you have sample X tilde, then that's it. This is the learning rule. You take X, you infer hidden states, you take the outer product, that's the positive phase. You run your Markov chain for a few steps, maybe just 1 or 2, get the negative sample. Once you have the negative sample, you infer the hidden states, and again, take the outer product between the two, which is the expression here. So in fact, to do learning for any type of undirected graphical model using sampling, the only thing that you need, particularly for RBMs, is you need the data, and you need negative data, right? The positive data is telling you this is the real data. The negative data is telling you this is the sample from the model. And what you'd like to do is you'd like to say, well, the distribution over those two things should be the same. That's the matching. That's what moment matching is. Effectively here, sometimes people refer to the first term as the expected sufficient statistics with respect to the data distribution. The second term is the expected sufficient statistics with respect to the model. And you're just trying to match the two expected sufficient statistics. And this is the learning rate. Now, So if I look at the contrastive divergence learning with k steps, again, you generate a negative sample x using k steps of Gibbs sampling, which is extremely easy to do with RBS. That's why people are using these kinds of models, because they just up, down, up, down. You generate the negative sample using k steps of Gibbs sampling, starting at a data point, right? So every time you start at a new data point, you run your chain for k steps. It's almost like taking the data point and corrupting it a little bit. And you go back to 1 until some stopping criteria. And some stopping criteria, typically people look at is other parameters changing. If the change in the parameters is less than some threshold, you stop. So this is known as a contrastive divergence with k iterations of Gibbs sampling. And generally, the bigger the k, the less biased the estimate of the gradient will be, right? Because k1, basically what that means is you start at the data, you just corrupt the data a little bit. So imagine this big exponential space you're working with, and your data lies in really small subspace, in fact, exponentially smaller subspace in this space. So if you start at the data and just do one step sampling, you're just doing a little bit of a corruption of the data and saying, locally, make sure that locally everything is okay. Typically, if you set k to be larger, then the model can start exploring the space a little bit better, right? It can move away from the data. And as you move away from the data, you want the model to say, well, the data that's far away from my real data should have small probability. And if you never go there, then you will never know, how much model, what mass model is deciding in the parts of the space that you never visit. So in practice, K1 actually works quite well for learning good features for pre-training. And you will see that you can actually learn very good features. You learn edges, and you learn interesting structure. And then in 2008, Tijman and Telemann showed that there's another algorithm that can actually work much better. It's called stochastic maximum likelihood estimation, or persistent contrastive divergence. And the idea between persistent contrastive divergence is that instead of initializing the chain at the data, you're initializing the chain to the negative samples of the last iteration. Right? So you start at the data, you do k steps, this is your negative sample. Right? Then you get a new data point. Instead of reinitializing this chain at the new data point, you just initialize the chain at the negative sample, and you keep going. Right? So basically now your negative samples never reset back to the data. They kind of wander around. And this algorithm, very simple, right? So X tilde comes from the previous iteration, right? So this particular algorithm was shown to work much better as a generative model because it can explore space much more efficiently. Although this algorithm has higher variance, right? Because typically if you reinitialize your chains to the data, you kind of start at the data. So the samples that you get, the negative samples, they kind of look like data. Here your negative samples could look like something arbitrary. So typically you have to reduce your learning rate substantially in order to be able to learn this model. But this is what, so here's what the MNIST dataset looks like. This is what you can learn using contrastive divergence. Oh, sorry. So these are the kinds of features that you can learn. And with persistent contrastive divergence, if you actually sample from the model, you can get realistic looking images. In fact, if I go back, how would I sample from the model? The way that I would sample from the model, actually the true samples from the model would be, I take my model, I don't have any data, I initialize my hidden states or my visible states randomly, some random configuration of pixels. And then I run my Markov chain, I run my Gibbs sample. I go hidden states, visible states, hidden state, visible states. And after about thousands of these iterations, you should start seeing digits. Because now the model is actually moving into the space of high probability. And you should start seeing realistic looking MNIST digits. And it's something that you will do in your homework to really see how well you can model, in this case, MNIST digits. Which turns out to be a fairly difficult thing to do. Right? This is not a simple mixture of Gaussians or something you can draw samples from easily. Yes?
When you say negative sample, you just mean the xk?
Yes, that's right.
Is that the definition of a negative sample?
It's what?
Is that the definition of a negative sample?
Yeah. So sometimes Yeah, it's the definition of negative samples. So maybe I can just clarify. The xk is a sample from your Markov chain, right? And so sometimes people call it as a negative sample because it's a sample from the model. Positive samples is sometimes referred to as the data, right? So the data is what you actually see. So you say this is truth. So you want to assign higher probability to it because that's what you observe. Samples that you get from your Markov chain are samples from the model, and these are fake samples. So sometimes these are called negative samples, right? And ultimately, this learning rule will come up, once you start hitting zero gradient, it basically, what happens is that the samples that you get from the model, the distribution of the samples should match the distribution over the observed data. Once you hit that point, then you have a good generative model. That's essentially what the maximum likelihood learning is trying to do. So this is what the features would look like. Couple of tricks that I want to go over. It's not very easy to debug training ORBMs using gradient checks because the gradients that you're computing are not correct, right? These are just samples. These are all based on just samples from the model. So instead, you can look at the approximate tricks. Some of them are good. Some of them, are not so good, but nonetheless. You can plot the average stochastic reconstruction. So given the data, you infer the hidden states, sample the hidden states, reconstruct back the original data, and see, is this reconstruction error decreasing? Ideally, it should be. It's not perfect, because there are some examples I can construct where this will not be true, but in general, it is true. You also want to visualize what kind of features that you're learning that are coming out of each hidden unit as if it was an image, right? Kind of like what you did for your homework assignment. And you should start seeing patterns. You should start seeing, because here you're actually building generative model. It's not the classifier that says, well, I see this one feature, it's a 2, and I see this one other feature, it's a 3. Here you're actually trying to learn features that allow you to actually generate images of 2s and 3s and 4s and 9s, right? It's still a very easy data set. But nonetheless, you should start seeing interesting structure evolving as you're training this model. And then you can also try, to approximate the partition function z to see whether this approximation decreases. And there are ways of doing that. I think later in the class we might go into one of those techniques, which is a little bit more elaborate. It relies more on a statistical method called annealed importance sampling. Which allows you to guesstimate or estimate the negative log likelihood properly. And so now you can monitor, are you really optimizing the likelihood objective properly? But for your homework, you can just look at the first and the second one. Really look at the reconstruction accuracy approximately, and also look at the visualizations. Are you learning something interesting? Any questions on this? Yes?
So we started out with the maximum likelihood objective, and then you said the second term of the gradient was trying to decrease the likelihood of the negative sample. That's not something that's naturally encoded in the maximum likelihood objective, is it?
No, it isn't. It is coming from the likelihood objective. Because the way you can think about this is ultimately I guess what I should say is that ultimately it's the difference between two expectations. Right? The first expectation is the expectation with respect to the data distribution. The second expectation is expectation with respect to the model distribution. So the two will be 0 if they're matching, right? But if you look at the likelihood objective itself, the first term is more like a positive. So if you want to increase the likelihood, you're trying to kind of move this up. And the second one, you're trying to move the other one down. So you're basically trying to match. If your model, like where would the likelihood be 0? If your model, anytime you sample, when you get samples from the model, they would perfectly describe your training data, that's when the maximum likelihood would be 0. Now, obviously, that might not be good because you have to regularize it. You don't want your model to just assign non-zero probability to your training data and 0 probability everywhere else, because that would be the maximum likelihood solution. So you have to smooth it out, right? And this is where regularization comes in and so forth. But roughly speaking, you're really trying to match the two distributions. And that's what these two expectations are doing. And that's the learning rule for Markov random fields, conditional random fields, any type of undirected graphical model. You always have these two terms that you're trying to match. Now, the other thing that maybe briefly I'll go over is you can start extending these models to other types of data. So here you can add a quadratic term to the energy function, right? So here you're adding this quadratic term, the last term, a half x transpose x. In this case, the conditional probability becomes a Gaussian, with mean given by C plus W transpose H. And the identity covariance matrix. And there's been a lot of work trying to model distribution of images. There is something that's called product of t-distributions or product of experts, and sort of extensions where your covariance matrix is not identity, but could be full covariance matrix, a low-rank covariance matrix. So it sort of gives you, you can be very elaborate what kind of structure you want to model in images. And then typically you have to normalize the inputs and so forth, right? Just like as we've seen before. And this is what, if you add this additional term, this is what the conditional probabilities would look like. It's just a bunch of product of Gaussians. But the marginal distribution is not Gaussian, right? The marginal distribution is a complex distribution. So you can model images, right? So here, given these images, you basically get that structure, right? From images of natural scenes, if you treat them as continuous real-valued images. And again, as I mentioned before, this is the case. You can think about it is that if you get a new image, and I say, what's this new image, how it's made up, it's just given by some combination of these edges, right? Anytime, you have that particular structure. Now, the other interpretation to have is that you can think of RBMs as a mixture of exponential number of Gaussians, which is an interesting interpretation, requires a little bit of thinking. It's kind of true, and it's a little bit of a bizarre interpretation, but it's nonetheless is a powerful one, right? If I look at the probability of V, where V is my image, I can say, well, it's the sum over H, the conditional probability of V given H, times the prior probability of H. I can always write it down this way, right? Now, notice H here. What is H? For this particular image, there are 3 hidden units. Each hidden unit takes value 0, 1. So there are 8 possible configurations, right? So if there are 8 possible configurations, then this P of V here represents a mixture of 8 Gaussians, right? Because each one, I know that this is a Gaussian. I know this is some complicated prior that I have to derive what it is, but it's the sum of a whole, over 8 Gaussians. If I have 100 hidden units, there are 2 to the 100 possible configurations. So this model is, a mixture over 2 to the 100 components. Now, the trick is that it's not quite true because they share a lot of parameters, right? It's not like I have exponential number of Gaussians where each Gaussian has its own parameters. These parameters are all tied together between these mixing components and these conditional probabilities. So P of H here is something is known as an implicit prior, right? So it's an implicit prior way to integrate over the states of the visible variables, which you can do for this model, but the conditional is given by Gaussian. So it really is an exponential mixture. And a lot of people would argue that these models are much more powerful than mixture models, right? Because they have this expressivity built in them. So they can model much more complex distributions than like a mixture of Bernoullis, for example, or a mixture of a few Gaussians. Here is another model where you can say, well, we can extend this model to modeling count data, where your data is no longer real valued, but it's counts. So for example, D here could represent document, K could represent vocabulary size, D could represent the number of words in the document. So just basically counting which words appearing in the document. And it's kind of, I've shown you this before here, given unlabeled data, you can discover these topics, right? So for images, you're discovering these edges. For textual data, you're actually discovering topics, which is interesting, right? Here's one-step reconstruction from the replicated softmax model. So it starts capturing some semantic structure between words. For example, this was trained on Flickr dataset. Like if I say chocolate cake, I give it as an input as chocolate cake, I sample the states of the hidden variables in an RBM, and I reconstruct back. This is my negative sample. You can think of what it's generating is a one-step reconstruction. So it's like a one-step contrastive divergence. So it generates things like cake, chocolate, sweet, dessert, cupcake, food, sugar, cream, right, birthday, which basically kind of says that these all are the words that are kind of similar to the data. I like particularly this one. There is a flower, high, and then there's a Japanese sign, and then it generates flower, another Japanese sign, high in Japan, Sakura, a couple of other Japanese signs, blossom, Tokyo, and stuff. So it's kind of capturing this notion of semantics, right, by just looking at co-occurrence. And again, this is a generative model, right? So if I say, sample me from this model, I can start generating. You can see it can, generate a whole bunch of different things. You can also use this model for recommendation. At some point, this is one of the state-of-the-art models for recommendation systems. So your observed variables are user ratings, right? Again, it's account data. So you say, are you rating this movie as 1 or 5? So V represents the number of movies. H represents your preferences, right? And if I look at the learned features that the model is learning, it kind of learns these interesting genre, right? There is like scary movies, there is comedies and stuff like that, which basically just based on the rating patterns of the data. It's very efficient, and I think it was part of the winning solution at the Netflix competition. Back in 2006, 2007, Netflix set up the competition because they wanted to improve their recommendation system. And whoever was able to improve the system by 10% would have gotten the $1 million, right? And there's like a whole bunch of teams, a bunch of ensembles. At some point, it became engineering effort to actually get there. But the interesting thing about Netflix problem is that they wanted to say, how can we detect whether the user is going to like a particular movie or not, or have accurate prediction? And initially they said, well, we're going to give $1 million to somebody who can improve the system by 5%, because they've been working really hard to improve the system, and it's like a pretty big gap. And they've talked to a whole bunch of people, and people said, well, maybe we should, just to be safe, on the safe side, we should make it 10%, because it's like a very big margin. And they were right, because once they released the data, within like 4 weeks, people improved by more than 5%, according to the metric that they've set up. So it was good for them to make it higher. So you can model different types of data modalities, right? You can use softmax, you can use Gaussian. There are a couple of papers that show extensions to modeling any other members within exponential family. You can model Poisson distributions, you can model gamma. Whatever your data looks like, you can model it. And it's easy to infer the states of the hidden variables, right? You can say the conditional probability is just given by the product of logistics. So it's exactly what you would do as a feed-forward neural network. That's exactly what you would do as a feed-forward neural network. Just a single layer feed-forward neural net. But you have this probabilistic interpretation, right? And you also have a generative model. You know how to sample from the model, and you know how to evaluate probabilities. For speech, this was also an interesting data set where this was done by Hong Lak Lee at Stanford, where they've looked at speech signal, and they basically were able to say that just by looking at the raw speech data, the first layer was picking up features that was highly correlated with specific types of phonemes. Or like here, it was basically capturing another example of a phoneme. So they basically, some hidden states started picking up phonemes, which was pretty interesting because you're not really telling the model that there's a thing called phoneme and it corresponds to particular this sound. It just naturally was discovering these low-level structures by just modeling the data itself. All right? So for images, you're detecting these edges, which we believe is the right representation. For documents, you're detecting these topics, which we believe is the right representation. For speech, it was detecting these low-level phonemes, which again, we believe is the right representation, right? Without actually using any labeled data, just by being able to model the data itself, right? The last thing I want to mention is this notion of the product. So the joint distribution is given by this expression, right? It's log linear. If I marginalize over the hidden variables, as we've done before, and you should go through the derivation, the marginal distribution has this product form, right? It's a bunch of soft pluses, product of soft pluses, right? Which is what you're seeing over here. So what does this really mean? let me show you an example. Suppose that in my data, I'm discovering these 5 topics, right? These hidden units corresponding to 5 topics. If I tell you that in my document, I see topics government, corruption, and mafia, then these topics will get combined to give a high probability to the word Silvio Berlusconi. You guys know who Silvio Berlusconi was? He's like a former prime minister of Italy, and he's like has, you know, friends in mafia. He's in the government. He's like a bunch of corruption scandals. I should probably add like he had like a bunch of parties with you know, underage teenagers, and was the prime minister of Italy, right? But nonetheless, so what does this say? This basically is telling me that each hidden unit specifies the distribution of the words, right? It specifies a topic. If I multiply all of these distributions together, I will have very high probability. I'll have a very spiky distribution. So I can be very precise what I'm modeling. And this is very different from mixture models, right? Or latent directional allocation, topic-based models, where I first pick a component and then I generate a word from it. Here you're really multiplying a bunch of different experts, renormalizing them, so you can have very spiky and very accurate distributions. And so typically these models work much better for information retrieval. So if I want to find closest article, or if I want to find something that's, you know, relevant to my, given a particular document, if I want to find closest documents, these models work much better. Okay? And this again comes to the problem, as we've seen before, local versus distributed representations. In local representations, like a mixture of Gaussians, right, or nearest neighbors, you divide your space into these subspaces, and for each subspace or for each partition, you have your prototype, right? But for RBMs and PCAs, sparse coding, autoencoders, factor models, factor analysis, for example, you really have this notion of, you know, as you introduce these hidden states, you're really partitioning the space, right? So you kind of saying that each parameter affects many regions, not just local regions. So roughly speaking, the number of regions grows, roughly speaking, exponentially the number of parameters, right? And finally, you can also take the original Boltzmann machine and you can add lateral connections in each layer. So some work with neuroscientists, because we believe in the brain, you know, neurons are not just connected to layers, there's also lateral connections. There's been some work of introducing these lateral connections that can, you know, serve as inhibition or excitation, which is to say, if H1 is 1, maybe H2 should be 1 as well, right? So you can learn that particular pattern. And here it's fairly straightforward. You're just adding these 2 additional terms, right? And when only one layer has lateral connections, the model is called semi-restricted Boltzmann machine. Right? So for example, there's been some work of modeling lateral connections in the observed data, but not lateral connections in the hidden states. So you can kind of like model more accurately the covariance structure in the data. And obviously you can use the same learning algorithms, the same learning rules to train these models. So there's tons of different application domains, natural images, people look at retrieval, collaborative filtering, people have looked at trying to model video, there is caption generation work, which is kind of, you can generate very realistic looking captions by using these models, essentially going to be converting them into some form of a recurrent network, speech perception and so forth, right? Like just basically building these local models and combining them into a deep neural network. And it's interesting, you have the same learning algorithm, you can basically deal with multiple input domains, right? So these models can be quite flexible. Okay, so let's stop, I think let's stop here.